There. Okay, I lost kind of losing my voice. This is not going to be my best video ever, but I'm going to do it anyway. All right, so here we go. Today we're going to look at 2.3, analyzing functions. And by analyzing, we're going to look at some key features, domain and range, something maybe we're familiar with, we've already done a little bit of, but also look at increasing and decreasing and symmetry and some different other things. All right, so let's begin with some terminology. And these are some terms you should know from previous years. To start with, just talking about what a relation is. A relation is simply a set of ordered pairs. And it's just basic relation. Now, when you look at this relation, there's a couple things we pay attention to. The domain, which is your input, which if you're thinking of a set of ordered pairs, it is the X part of the ordered pair. And that X part is always your independent variable. That's independent. The range is going to be your output. This is what you get from the function based on your input. It's always going to be the Y part of the point, and it is dependent on what you put in for X. Now, if this relation is a function, or really to test if it's a function, then you would not want your X's to repeat. So as long as your X's don't repeat, you've got yourself a function. And there's a reason for that we'll dig into later, why you're concerned on whether it's a function or not. Now, let's look at a particular relation here and just pick out our domain, our range, and determine if it's a function. So the domain are all the X values. So that's going to be your 1, your 2, your 3. When you list your domain, we typically like to list it from least to greatest. So I'm going to go 1, 2, 3. Your range are your Y values. So that's your 6, 6, and 8. Now, no reason for us to write the 6 twice. We just write one time. And then to decide, do we have a function? Well, did your X's ever repeat? Nope, they did not. The Y's did use 6 twice, but I don't care about that. I'm only paying attention to the X's. So yes, this is a function. Let's look at some graphs and determine the domain and range. Here I have just a whole bunch of ordered pairs. So this kind of is like the previous one, but it's set up like in a graph format. And since I do want to keep them sort of least to greatest, I'm going to go ahead and start with my domains, my X's. These are going to be the blue numbers. I'm going to start over here on the far left and go this section, picking them out in order. So if I pick out all the X's, I see there's a -1, 0, 1, 4, and 5. Now, I never did have to repeat X, so I feel like this is going to be a function. By the range, they're going to be your Y's, the red numbers. So they're Y's, so I'm going to start at the lowest, that's a -3, and work my way up. -1, 1, 2 is there twice, don't need to write it twice. Also, don't care that it repeats because it's from the range. Now, more likely in college algebra, we're looking at these other 3 types of graphs. And I really like this one, and I like the way it's set up because when you're doing domain, you're looking at your possible X's. Now, this function, though, is a continuous. It continues on. There's not like distinct points on this. It's a flowing, continuous function that I don't have like these stop parts to it. So because of that, my domain is going to be points. I'm going to list it as, and so I look at what are my possible X's. Well, I'm looking at how far left and right it goes. What is the farthest left? That's my lower bound. What's the farthest right? That's my upper bound. So that's a -4 to 4. And since it actually does hit -4, we would be using brackets on that domain. Same idea with range, but you're looking at your Y's. So you're looking at what's the lowest it gets. It's a -6. The highest is a +6. If you look at C here, you see that there's some arrows on these. So this is indicating that this is going to continue on forever. And if you think about it continuing forever, that means it's going forever left and forever right. But it's also going forever up, down. So really this is a classic negative infinity to infinity domain and range. The next one's similar, not quite the same, sort of a combo of those two, ellipse there and the line. When I look doing this, because of the arrows, this is going to continue wider and wider and wider, so it will go forever left, but it also goes forever right. That is not going to be the case vertically, though. It does have a bottom point to it, so the lowest it gets is -3, and it does hit that, so bracket, and then the arrows indicate that it will go forever up. All right, so that's kind of our domain and range. Right, so let's talk about what determining whether it's a function or not. We know that that means that we don't want our x's to repeat. Okay, but what's that mean when you're looking at a graph? Well, when you look at one of these graphs, to have your x repeat, it would mean that you'd have a value like right here. And so that has an x value of 2. And somewhere else on the graph, you have another x value of 2, like right here, for instance. Well, so if that were to happen, what we can use is what we call a vertical line test to check to see if it's a function. And that's just a quick way to test. If you can take a vertical line and it touches the graph in more than one point, then the graph is not a function. Because if it touches in more than one spot, it would indicate that it's got the same x value in more than one spot. So for this first one, so we're just saying yes or no. Is it a function, not a function? So right here, if I were to draw a vertical line, it would hit here and here because both of those spots have an x value of 2. So that's what's going to make this not be a function. So you're running a vertical line all the way, seeing if it'll ever hit your graph more than once. This next one, nope, no vertical line would hit it twice, nor will it on this last one. As we talk more about functions, we are also going to start using what we call function notation. And that's just a special notation. It still is going to mean the same thing as an x comma y. And we will still use x comma y, but it's just another way to show it. So instead of xy, we might write it as x. Instead of y, we write f of x, like that. And so f of x is really the same thing as a y. And I'm not tied to f. I could use any letter. It's just f is kind of our go-to letter for functions. So here I've given us a function. I called it m of x. And it's an m function with respect to x, meaning x is going to be our variable over here. And we're just going to do some evaluating. One of the reasons we like this notation is because it's really quick and easy to show kind of a task that you want to do. Right here, I want to put -3 in for x. So right here, I'm replacing this x with a -3. So in my equation over here, I'm replacing this x with a -3. It will look like this. 3 with a -3 squared minus 5. And then we've got to do our order of operations, do inside those parentheses and power first, and then go ahead and multiply. That's a 27 minus a 5 is 22. All right, let's try one that's a little trickier than that. This next one is an example where I'm not really putting in a number. I'm going to put in an expression. Well, if I try to plug an expression into it, I'm going to get an expression back. Now, I have edited this since, but this I don't have enough space here, so I'm going to move this up to here. Maybe it's already there on your notes. So here we go. M of x plus 2. So that means I'm going to put in a 3, and then put instead of the x, I'm putting in an x plus 2 squared minus 5. All right, so now I just need to clean this up. I've been pushing you pretty hard on using some mental math to square binomials. The number one rule is you never distribute a power. That does not work. This is not x squared plus 4. there's going to be a middle term. And so to square this, remember we square the first term, multiply the 2 and double it, and then square the last term. It will be a trinomial. So what I'm going to do now, we've been doing that for a few weeks now. What I want to do is be able to square that and also take the 3 and distribute it. Now, I can't distribute the 3 first because this power has to happen first. So I'm going to square it and then take it times 3. So the first term would be an x squared, but I got to take it times this 3. So it's going to be a 3x squared. Then I multiply these 2 and double it. Well, that'll be a 4x times 3. That's a 12x. Last step is to square this term. That's going to be a 4, but I'm going to also take it times a 3. So that's a 12 minus 5. All right, we're trying to get a little bit more efficient than what we were doing in Algebra 2. And so that's why I'm kind of pushing you to do these shortcuts. You're going to run out of time on tests if you do everything the long way. So we're trying to amp up our knowledge here. All right, so let's try evaluating functions, but looking at it graphically instead of algebraically. So this graph is showing the progression of a disease, the average number of T cells, f of x. So T cells is going to be our f of x or our y value, is a function of time after the infection. So x is going to be our time. So along here is our time. Here's our number of T cells. And you can see since we've got the infection, the T cells are declining. We want to use our graph to find f of 8, right? Well, 8 is just what we're putting in for x. So we're going to replace x with 8. So when we look down here at our x value and go over to 8, I'm looking what does the function equal at x equals 8? And I go up and it looks like, oh, that's 200. So then f of 8 is actually going to equal 200 T cells. Let's try going the other way. For what value of x is f of x equal to 350? Right, these are classic ACT kind of questions, really maybe more science questions where you're having to interpret values on a graph. And what this is saying is that the y value needs to be a 350. So now I'm coming over here. 350 doesn't fit perfectly on here, but midway is 300, so 350 is about here. I'm going to go over, and boom, I think I hit it right there. So that happens at 6 years. So I would say 6 years. Okay, so let's move on past domain and range, and let's look at another feature. Let's talk about increasing and decreasing functions. All right, when we're dealing with functions, they typically will represent some scenario, and oftentimes you're looking at when that scenario would be an increasing function versus when is it decreasing. And so to look at that, increasing functions are going to happen when a graph is going, what do you suppose? It's going up. From left to right. So you're headed up, you're going uphill, it's positive slope, whatever you want to think of. A decreasing function is when the graph is going down from left to right. So it would have a negative slope where you're headed downhill. Now, not functions typically, I say typically, whatever, our functions are going to be a little fancier than just always being increasing or always being decreasing. We're going to probably have some that have a little bit of both going on in there. Oh, and it might even be constant, where it's like a horizontal line and it doesn't increase or decrease. All of that's fair game. Now, the tricky thing about increasing and decreasing, and I can't express it enough. In fact, if you had a highlighter, I would highlight it. Always use the x values. My question was looking at when it's increasing or decreasing, and when is a time. And remember, time is your x. So I'm looking at x values to pay attention to when it's headed upward or when it's headed downward. I don't care how far up it goes or how far down. It's when is that happening. So looking at this first example, I start from left to right. I'm looking left to right. Is it going up or going down? So left to right, I am headed down, 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 down until I get to here. And this X value is 0. So I'm going to say that this is a decreasing function from, oops, let me change that out. From negative infinity until I get to 0. And then if I start tracking it, now it's headed up, 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 until you get to, what do you think? Not 4. I don't care about the Y. I'm wondering how long is it increasing? And it's increasing in this interval right here. From 0 until I get to 2. That's when it's increasing. So from 0 to 2. Oh, you know what? I forgot to mention. When you're doing increasing and decreasing, you always use parentheses. You're not really caring about the or equal to, does it actually hit that spot or not hit that spot? We don't do brackets, we do parentheses. And you don't really do that U shape either. You'll use commas typically. So now I'm back to my function. Sorry, that was a side note. So now I got to here, and now I'm headed down, 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 down. So I'm decreasing the rest of the way from 2 until I get to infinity. This is going to be a decreasing function. So I'm going to say from 2 to infinity. And this one never does flatline. So I write NA or something like that for not applicable. It's never constant. All right. See if you can do this next one. Do it on your own. Mark intervals where it's increasing or decreasing. All right, here's what I got. Do you got the same thing? All right, let's try something a little fancier than that. This is really the one I should have you do on your own. So I'm gonna have you pause the video and do your increasing and decreasing. Come back when you're done. All right, here's what I got. Did you get the same thing? Big thing here is I was checking to see if you got your X values here. So this is an increasing, or I'm sorry, a decreasing function until you get to, don't say -1. I don't care how low it goes. I'm concerned with at what stage on the X-axis it stops decreasing. And that happens at -2. So decreasing from negative infinity to -2, and then it increases not until you get to 8, but until your X value is 1. So you are tracking this along the X-axis. It increases till you get here, and then it's a constant the rest of the way. Here might be an example where it might make more sense why we're paying attention to those X values. So this is a graph. It shows, and there's a lot of wording. I maybe have even deleted that from your notes by now, but I'm looking at this. Your X-axis is in time, measured in minutes. Y-axis is height in feet. And what you're doing is you're just flying a kite here. So I've got some questions for you from this flying a kite. What is the maximum height of the kite? Okay, height is your Y value. So you're picking out what's the highest you ever see that get, and it looks like it's right here. And so what is that maximum height? Looks like that would happen at a 175 feet. When does that happen? Okay, the when is your X value. So at that height, you come down and you can see, oh, that happened at 5 minutes. Now we're going to talk about the increasing, decreasing constant. So when is that kite's height increasing? Well, the when is what it's all about. It's the time. So it's increasing from 0 to 5 minutes. So I'm going to say increasing from 0 to 5, but then it immediately starts decreasing from 5 minutes until you get to, it looks like about to right here, which if I track that down, looks like about 10 minutes. So it's going to decrease till 10, and then you're back up again to about right here. which looks like maybe 15 minutes. Okay, so let's fill that in. Increasing until you get, or I'm sorry, decreasing until you get to 10, but then you're back up to increasing. So back over here from 10 to 15. And then what happens? Well, you can see it's flatlining. So it is constant from 15. And how long do you think it's constant? Looks like just another 5 minutes there. So till 20. And then at 20 minutes, you can see it just decreases. So 15 to 20, and then back over to decreasing from 20 to 25 when it lands back on the ground. Hopefully that helps you think X values always on that increasing and decreasing. All right, so the last thing that we're going to talk about today is symmetry. And symmetry is a geometry concept probably that you would remember. And you typically in geometry, we're looking at graphs or polygons or something like that, some sort of a shape, and looking at symmetry. So I know your notes are probably not color coded, but it does sort of help you to see the color coding. So if this blue part was my graph and it reflected down here, you can see that it is reflecting over the x-axis. So we call that x-axis symmetry. On this one, you can see that the blue part kind of flips and matches over here to this side where it's the red part, and that is called y-axis symmetry because it's folding over that y-axis. And then the last one is maybe a new concept. It's called origin symmetry. And what the origin symmetry does, it actually does a rotation. It's a rotation 180 degrees, and it's going to land over here. This point right here rotates 180 degrees. It's going to land right there. So it's rotation over the origin. We call that origin symmetry. Now, looking at it, not a big deal to tell the symmetry. Let's try, we don't want to have to graph every single thing though. So we want to look at some of these algebraically. So there's a relationship you want to notice here. If you look at some particular point, XY, so I'm going to pick this point as my XY point. It's going to have a reflection point right down here. If this is XY, can you tell me what this coordinate would be? It would still be X, but now it's negative Y. So that's what we want to do here. If XY is on the graph, so is X negative Y. Now you can also tell with it having an x-axis symmetry, it's always going to have this point straight above this other point, which means it will never pass a vertical line test, which means x-axis symmetry will never be a function. All right, let's try that same idea on this y-axis example. So here's my point over here. I'm going to call it x comma y. What do you think its matching point over here would be? Well, hopefully you're thinking in your head, well, it'd be a negative x, but still a positive y. So you're just going left instead of right. So if xy is on the graph, negative xy is on the graph. Now that one is a function. And origin symmetry also going to be a function. You can look at it and see that. Here's my point, xy. And if you rotate that 180 degrees, it lands down here. What do you think that ordered pair is? It's negative x, negative y. Now that little relationship that you have with these x's and y's, that's what we're going to use to determine algebraically if they are, which type of symmetry your function might have. So look here, you're going to look back at this slide as we do the next few slides, but well, never mind. I think I have it written. I'm going to just practice some very basic ones. First of all, can you look at these and tell me what type of symmetry they each have? I'm an A. What do you think? Ideally, you see this as your line of symmetry, and this is y-axis symmetry. What do you think on this next one? All right, this actually is one of these determine what type of symmetry, if any. This one does not have any symmetry. It's got to reflect over this line and it doesn't, or reflect over this line and it doesn't, and it doesn't have that rotation thing either. Now this looks like an absolute value graph and it can have symmetry. This particular example though does not. So there is no symmetry on this. And what about on C? What kind of symmetry there? It has all three. You can see it reflecting over the x-axis. You can see it reflecting over the y-axis, and you could even do a 180-degree rotation. This has all three types of symmetry. Now, of course, because it has all three types, that means it has x-axis symmetry, which also means it's not a function, which you should be able to tell, yeah, the circle is never going to pass a vertical line test. Now, before I dig into actually looking at some algebraic functions to determine their symmetry, there's another relationship that we use. We call functions either even functions or odd functions. Now, they might be in neither situation. They might not be either even nor odd, but even functions have y-axis symmetry. And remember, y-axis symmetry looks like this. If you have an x and a y, you also have a negative xy. That's y-axis symmetry. Odd functions are going to have origin symmetry. And remember the relationship there with your xy and your negative x, negative y. Both of those points would fall on the graph. Now, you might have thought, oh, that was going to be x-axis. Nope, because we're looking at functions, and x-axis symmetry is not a function. So it couldn't be an even function or an odd function because it's not a function. So even functions have y-axis, odd functions have origin. Okay, so here's the deal. This is, I know, going to be tiny on your notes. I apologize. But this is how you test whether a function is going to be even, odd, or it might be in neither situation. If you have an even function, you're going to replace the x with a negative x. And if you do that, your hope, I guess, is that the function will come out with all the same signs. In other words, if I plug in a negative x, I did have a y, I'm still going to have a y. Everything is going to still be the same. But look at your odd function option. You're still going to replace x with negative x, but on an odd function, the function will come out with all different signs. Every sign will be the opposite of what it used to be. Maybe I should be writing opposite signs. That might be a better option. But each sign is different than the one before it. So the way that's going to look is when you put in that negative x instead of that positive x, the y values, every term is going to be the opposite of what it might have originally been. Now, you might have a neither scenario, happens all the time. That means when you replace the x with a negative x, neither of those above scenarios happen. So you might have some of the same signs and some of the different signs, kind of a little bit of both going on. All right, so here we go. We're going to test for even and odd functions algebraically. So even functions, again, even functions are y-axis symmetry. Here's the relationship. If you put in a negative x, you should get the same thing back as if you put in a positive x. If you put in a negative x, but get the opposite thing back as what you used to have, then that's going to be odd or origin symmetry. Let's try a few. Here's how this looks. Instead of going f of x, I'm going to do an f of negative x, which means I'm going to put negative x in for all of the x's. And then I'm going to simplify it. A negative x cubed is just negative x cubed. And then this minus 6 times negative x is going to turn into a positive 6x. And now you check, how does that compare with what I started with? Well, the x cubed is the opposite sign, and the 6x is the opposite sign. All right, if everything changed, that's an odd function. And tells me also it has origin symmetry. Let's try again. On this one, I'm going to plug in a negative x and see what happens. If I put in a negative x, take it to the fourth power, minus 2, negative x to the second power. And now let's work through and simplify, get rid of your parentheses. If I were to take a negative x to the fourth, that's going to end up a positive x to the fourth. And then I'm going to have a negative 2, and this is going to turn into a positive x squared. So end result, x to the fourth minus 2x squared. Now compare that with what we started with. X to the fourth minus 2x squared. Oh my, it matched perfectly. So that's this scenario. When I put in a negative x, I got the same exact y that I had originally. So this is going to be considered an even function. All right, we've got one more to try. Let's see how this plays out. So h of negative x, put in a negative x here, square it, minus a negative x, oops, sneak in that negative x right there, and then a plus 1. Now we're going to clean it up. A negative x squared is going to go back to a positive x squared, but this is going to go minus a minus, which is going to turn into a plus x, and then a plus 1. And now you compare it back. The x squared, still an x squared. The negative x, now is a positive x. So I had one that stayed the same, one that varied, this one stayed the same. But when you have a sum of everything going on, that's a neither. That is not an even function nor an odd function. Now, it could still be a function. It's just not going to have y-axis symmetry or origin symmetry. Now, having done 3 of those examples, what I'm kind of was hoping you were going to do is start noticing some patterns with that. Can you figure out what really, when you made that negative irrelevant, you put in the negative x, but it didn't matter because it kind of went away and went back positive. What made that negative irrelevant? And I'm hoping that you're thinking, well, that happened every time the power was an even power, because that even power, whether it's squared or to the fourth or sixth, whatever, makes that negative go back positive. So if you have a function that has all even exponents, then it's going to be an even function and have that y-axis symmetry. Likewise, if you have a function that has all odd exponents, this is assumed to be a 1. If it has all odd exponents like that, then that's going to force every single one of those signs to switch. So if all odd exponents, if you every switch, that's considered an odd function and would have origin symmetry. This last example here, notice that it has an even exponent. It also has an odd exponent. So that's a scenario of a neither, because you have an even and an odd. I don't know what you want to do there. Maybe circle that. That's an even. That's an odd. So you have both even and odd. That's going to be a neither situation. Okay, so the tricky thing, that's actually super handy, that now you can determine even and odd. Now, I should say this doesn't always work. It works great on these nice polynomial functions like this, where you just have nice powers that you're dealing with. If I throw in a square root or an absolute value, now it's not quite as straightforward. But if all you're looking at is something with some powers, it's a great handy little trick. Here's the one thing, though, that you got to catch on to. I should have made note of it up here. I don't know why I didn't, because we were talking about even exponents. So, but look, did you notice that this here is a 1? Well, that doesn't really matter because I never plugged anything in for the x. So this is that's gonna stay a +1. That's not gonna change. But if I had done it down here, it also wouldn't have changed. And down here, I did want it to change. So that would have been a problem. So what we're referencing here is that constant term. A constant term is actually an x to the 0 term. If you think of this 1 is really a 1 times x to the 0 power. And a 0 is an even number. I have a 4, a 2, and a 0. Those are all even numbers. If you have a constant term, then that is considered an even exponent. And so keep that in mind. Works great if you're shooting for an even function. But if you're thinking you got an odd function and then all of a sudden I add a constant out at the end, that constant is considered an even. So then you'd have odd, odd, even, and I'd be back to a neither situation. All right, that's all I've got for you. Got to give my voice a rest. I am hurting. All right, hope this helps. Have a good day.